plotting position versus time. So what we're going to only do here is that we're going to only focus on constant velocity motion here. In the next chapter, I am going to talk a little bit about changing velocity, but what you're going to see here is that I will modify it, slightly, but it's really in the next chapter where I'm really going to spend a lot more time on that. Okay, so let's do this here. So we all know the mathematics of straight lines, right? So the mathematics of straight lines is this. We know that if I have an equation of a line, it looks like this. And what we're really saying here is that when I plot this thing, there's going to be some intercept, and this line here is going to have some slope. And what we know about the slope is it's the rise over the run when we're plotting y versus x like this here. So what we want to do here is that we want to apply this information to our situation where we look at our velocity equation. And that's what I want to focus on. We want to focus on the velocity equation. So when I look at the velocity equation, one of the things that we look at here is that we look at the following thing. So the velocity is defined as v instantaneous, which we just call v. This is literally the derivative of this curve. And so this actually represents what is called the tangent to the curve. But for the moment, when we plot things like this, we don't go after the instantaneous velocity. What we go after is we go after what's called the average velocity. And the average velocity, I have textbooks either draw it like this, or I have a tendency to write AVG for the average. And this guy is literally the difference in the position over the time interval. So this is what we really say when we're plotting this guy right here. So let's go look at this thing here. So a couple of things here is that, so when we do this is that I want to talk about the time interval briefly. So when I write a time interval, it's typically between 2 points that we write it out at. And what they do here, what's customary is to do this. They take T1 and they set this equal to 0. And when they do this, it's now customary to take T2 and redefine it as just T. Okay, so this is very, very, very customary. So if this is the case here, then look what happens now. What I'm going to do now is that I'm going to take my equation now. So I have now, so starting with V average is then delta X, delta T. And so there is 2 different points for the displacement, but our time now, because we define T as equal to 0, looks like this here. So now if I do a little bit of algebra, what you're going to find here is that it's going to look like this. I can rewrite this as x2 equal to x1 plus V average T. So now I have a linear equation, just like the one that we just wrote up above here. And so what you're seeing here is that this guy's telling me what? This guy right here is the intercept, and V average is the slope. And that's what I want to focus on. So let's go do that here. So what I'm going to do here is that I'm going to break this up into cases so that I can actually interpret what I mean by this here. So I'm going to start with case 1. So if I have case number 1, I want to start as simple as possible. I want to start with the stationary object. Okay, so if I have a stationary object, then clearly the average speed of this object must be 0. Right, it's not moving. So what does that mean here? If I take my equation and I plot this for a stationary object, so now I'm plotting x versus t here, that means that the object, let's say, at t equal to 0 is located at x1. And after a certain amount of time, since the car hasn't moved, x2 here must be at the exact location here. So my line here is that I get a stationary object implies that I have a horizontal line that's parallel to the time axis. So in other words, if V average is 0, then this implies here that x2, which is x1, will then give me 0 times t, and so clearly it's the same for all time here. So that means, this tells me here that there is no slope. So anytime you see a curve, no matter how complicated the curve is, if that slope is horizontal, then that means that I have that object is not moving. So there is no slope, which implies that the object is at rest. And sometimes that can be quite tricky here. Let's look at case 2 now. Excuse me. So now we're going to have a moving object with constant velocity. So let's look at that guy. So what do we know about key things about this thing here? Well, we know that if we're moving at constant velocity, then that means here, so constant velocity implies that the slope is equal to a constant. Now, what you find here is that the slope can have 2 different directions, right? I could have a positive slope, and if it's positive, that means it's moving to the right. However, if it's negative, that implies that it's moving to the left. So when I look at that graph, it's telling me that. So let's go plot this thing here. So what you're seeing here is that it looks something like this here. So if I start off at some point, let's say that this is point 1 for the red. And what you're going to see here is that if I have a positive slope, then that means this point 2 here, that this line then tells me that I'm going from point 1 to point 2. Now, let's be careful here. Okay, let's be careful, because if I'm plotting this, what does this mean here? Well, what this means here is that this point here is really x1, and this point right here is really x2 right there. So note that there's a line right here that looks something like this. So if I look at my line, this line from here to here, that purple line represents that I have 0 velocity. But note, there's a height change in here. That height change is given by what? Well, this height change tells you that if I start off at x1, and then I move to x2, how do I go from x1 to x2? The only way I can move is that if I travel some distance. But what's that distance given to? It's v average over that time. So you're seeing, what you're really visualizing here is that you're seeing that this little piece, this little area, is really given by this guy right here. This is what increases the distance. And that's what this line is telling us right here. Okay, so physically, that's what that equation is telling us. But now, let me redraw this just a little bit more so that I can be a little bit unified in how I explain this here. So here I go. So what I'm going to do here is that I'm going to draw two curves. So if I draw two curves, what does it look like? I'm going to redraw the red one. So the red one says I start at 1, and then I'm going to go up to here, to 2. So my curve then looks like this. The fact that this has a positive curve, right? So the red curve implies that you have a positive slope, which then implies that you're moving rightwards. So if I look at the motion diagram, I'm going to do this here. That motion diagram then says that I have dots that, let's say, look like this. And if my dots look like this, then my velocity is looking like this. And I'm going to call this the positive direction, which is towards the right. But now I'm going to draw a different curve. And this curve is then going to be the green curve. And so when you look at the green curve, what you're going to see here is that this curve is actually much steeper. This is 0.3 and this is 0.4. So when I draw this curve, it looks like this here. But wait a minute, you could see that this slope is negative. If this slope is negative, then this implies that it's now moving leftwards. So when I look at my dots here, you could see here is that when I look at this position, look at this line right here. This is really 0.1 right here, right? Look where 0.3 is at. 0.3 is very far to the right. So when I look over here, maybe I can draw 0.3 over here because it's much farther to the right than 0.1 is. But because it has a steeper slope here, then that means that that my dots are farther apart. So when I look at my arrows, these arrows have to be what? Longer. And so then these velocities, the speeds are higher, but now I'm moving in which direction? I'm moving in the negative direction, which is to the left. So each of these curves has a motion diagram associated with it, and it tells you a picture. So in this case, what do I do? For the red curve, I call this plus V. And maybe I should call these 1, 1, 1, 1. And then if I look at these guys, and if I try to write this velocity, maybe I should label these 3 because it starts at 3. So when I write this equation, I have to put a minus sign in 3 to tell you that you're moving in the leftward direction. What you're seeing here is that we started plotting position versus time. And the definition of the average velocity is that I have some interval of position over time here. And from here, I can rewrite this equation where I set t, I started the clock at some point. And so I have this linear line. So it's important that we start to interpret all of these details here. And the way we want to interpret them here is we want to interpret them by effectively doing what? We want to be able to understand what these curves mean. Okay, so if I have a stationary object, then clearly the velocity has to be 0. So if from that equation of the line, I see that x2 must be x1 plus 0, which then tells me that x2 and x1 are exactly the same. In other words, the change in displacement is 0. So when I go and I graph that, x1 and x2 is then drawn as a flat line. That is a line with no slope. But a line with no slope implies that there's no change in the displacement, as we see right here. So from now on, even though I have a complicated curve, if there is no slope to that line, that means that there's 0 displacement at that point. And if there's 0 displacement, the object must be at rest. Okay, now let's move on. So now I have a case where I have a moving object with constant velocity. So if I have a moving object with constant velocity, what we're going to do then is that we find that there has to be a change in displacement. That's what we mean by a definition of a moving object. So graphically, how do we see this? Well, remember the previous example in case 1 where we had an object at rest. The violet line here is my 0 velocity line. But if I've changed displacement, in other words, I have some delta x, then this red line implies that I must have a non-zero velocity line. Okay, so what does our equation says? Well, our equation says that x2 is equal to x1 plus the velocity times the time. And if I clean this up, you could see that this delta x right here must be equal to the average velocity times the time. In other words, it's this average velocity, of course, that's cause of the displacement. I'm not saying anything that you don't already know. Of course you know this, right? Of course you know this. So what we're doing here is that we're setting it up so that we can physically see what we mean by this stuff, right? We're trying to draw pictures that are really clear, that are easy for us to understand here. So now let's go look at this thing. So the reason why there's this height change in the position versus graph is because of this term right here. That is the cause of the displacement. So what I want to do here is that I want to explore this thing to get a better physical feel for this equation. That is graphically. So what I want to do here is that I want to consider two different cars, a red car and a green car, and they both have different speeds. So it turns out that the green car is moving faster than the red car. So because the velocity is smaller, I'm going to have a smaller change in displacement, or a smaller displacement. However, the green car has a higher speed, and of course, if it has a higher speed, it's got to be doing what? It's got to have a bigger distance change. So the question is, how do I write that now? Okay, so the way I draw this thing here is that I'm going to come in here and I'm going to set up my curve. And I'm plotting position versus time. So what I'm going to do here is that I want to be very, very careful on how I set this thing here. So the first thing that I'm going to do here is I'm going to draw an origin. So on my curve here, I'm going to say that this location right here is my origin. So if this is my origin line, you could imagine that if I have my green car starting at the origin, I'm going to give it some initial position here. So on the graph, it looks just like this. Now, if I have a red car and it's some distance from the origin, let's say that it's this distance right here. So you could see that the initial position of the red car is not at 0. And maybe I draw a point right here. And this point here is what I'm going to call x1 initial here. Now, you know what? I think I have to go back and change my notation. Note that right here, I wrote x2 naught, but right here, I wrote x1 naught. So what I'm going to do here is I'm going to come back and I'm going to erase that. And so that I'm sticking with the same notation, I'm going to write this as 2 initial, 2 initial. So what I'm seeing here is that if this car, the red car, travels a slower speed, it's going to cover a shorter distance in the same amount of time. So maybe this car gets to x1. So how about this car actually moves towards x1? So when I'm looking at this displacement, I could see that this displacement here is going to be a smaller value. But I'm going to assume that the car takes a certain amount of time to get here, and I'm going to say that this is the point time right here that both cars are going to travel. They're going to travel for some amount of time. So what that means here is that at this point, this is literally x1. So if I come in here and I draw a slope from this point to that point, what you're seeing here is that I'm going to get a straight line that looks like this. So this guy tells me about V1 average. And you could see here that when I look at that speed, this speed at this point is about that length. And so the slope is low. But if I have a car that's moving faster, then I could imagine that, of course, it has to travel a farther distance. So when I look at this distance between these 2 points here, you could see that that is a higher, that's a larger distance. So when I go and I look at my point x2, it's located here. So when I'm looking at this guy and I draw my line from the origin to there, what you're seeing here is that this line is what? I have a slope that's definitely bigger, and that represents my speed 2. So what I'm finding here is that this car has now moved farther away because it has what? A higher velocity as it's moving at constant velocity here. And so what you're seeing here is that these positions are telling you how big of a displacement this is. And that's exactly how it looks like on the graph. Okay. So now what you're seeing here is that clearly the key points of this thing, if I was to just briefly summarize this thing, right? So in summary, I mean, clearly one point here, of course, x2 is greater than x1. The green car was traveling faster. Another thing here is that the slope of the green car is steeper. And it's the steeper slope that tells me that I have a faster speed. On the other hand, the slope of the red car is less steep, which then tells me that it must be a slower speed. Okay, so now what I want to do here is that I want to go in and I want to talk about the slope. So the slope tells us two things. So what you find here is that it tells us, so if I look at the slope, there's sort of like a magnitude to the slope. And that's what we just looked at here, right? This tells us that if it's steeper, you're moving faster. If it's less steep, you're moving slower. But it also tells us a different thing. It tells us about the sign of this thing. And what we find here is that the sign tells us two things as well. It says that if I have a positive slope, that really means that we have the plus sign. And sometimes we say the positive slope may be going to the right, but I don't really want to get into that. We just want to say that positive means the way you've defined positive. And the negative slope, which is negative, is typically telling us that we're moving to the left, at least in this scenario here. So what I want to do here is that I want to go in and I want to look at this thing graphically. And we kind of touched upon this last time, so I'll try to move through this fairly fast here, is that I can have an object that starts at this point here, and it moves towards this point here to here. So what this is telling me is that when I draw this line here, what you're seeing here is that this guy is a positive slope. So if it's a positive slope, what this really means here is that this guy is moving to the right in this direction, right? And because it's a constant slope, of course, it has that speed here. Now, I could have another situation where the slope is steeper. Maybe this is 0.3 and this is 0.4. And when I look at this slope here, what you're seeing here is that it could go like this. And it could actually go right through the coordinate axis, right? But what you're seeing here is that the green slope here is a negative slope. So this negative slope tells us that we're moving in the negative direction. So in other words, it's moving in, let's say, this direction. Now, the fact that this slope is steeper, of course, I'm going to have a higher speed. And let's say, for example, that this is the origin, right? Right here, this represents the origin. All this is saying here is that the origin that we're crossing, what we defined as the origin, that doesn't mean that it doesn't have a speed there. it continues to move, in this case, past the origin in this direction here. So in this picture here, we would then write that this is a positive velocity. And in this case here, we would write that this is a negative velocity. So you get two pieces of information from here. Now, what I want to do here is that I want to go in and I want to look at the next piece here. And the next piece that we want to look at is we want to talk about the changing of velocity here. So let me make sure that I organize my thinking here. I'm not sure what I wrote up here. Did I label these? Yeah, case 1, case 2. So I should call this case 3. So let's write this case 3. So now I want to talk about changing velocity. So when we're talking about changing velocity, well, the only kind of change in velocity that we've talked up to this point is about speeding up or slowing down. So in this case here, we're talking about changing speed. So we change speed, but we have constant direction. So the only change that we're talking about is when we have change in speed. No change in direction. So immediately that tells me that I'm either speeding up or I am slowing down, right? So what do I mean by this thing here? Well, for starters here, we know what we mean by this in terms of the picture. So if I look at speeding up here, picture-wise, what I'm really seeing here is that I'm looking at my velocities. So if I look at my velocities, you're clearly getting longer and longer vectors here. But what does that mean? Right? So if I look at this has V1, V2, V3. What this really tells me right here is that when I look at the little interval for x1 versus the interval for x3, I'm seeing here that the big difference here is, of course, the displacement. But wait a minute. If I have this guy, what this really means that this has to have what? What you're seeing here is that, how do I say this? What you're getting is that clearly the slope here is steeper and this slope here is less steep. So what we should be plotting here, so when we go to plot this, so plotting changing velocity implies changing slopes. So I have to see changing slopes in order to really plot this thing properly. So let's go look at this thing here. If I look at speeding up, what should it mean here? So if I have a curve that looks like this, and in this situation, we're going to talk about speeding up. Well, I have my position, I have my time. And so my picture here, if I look at this red picture, what am I actually seeing here? What I'm seeing here is that I start off at some point. Let's say this is my point. And what I'm going to do here is that I'm going to assume here that there really is, at this point here, that we're starting at rest. So that means if I'm starting at rest, the slope at this point right here should be flat. So in essence, I have a dot that then looks something like this here. It has to be flat. And then it starts to speed up at point 1. So if it starts to speed up at point 1, then that means that the next point has to have a little bit of a slope change. So here it's flat, and then now this line here is, you know what, I shouldn't be putting arrows on here. And then what you're seeing here is that it's getting steeper. But if it gets steeper, then what you're seeing here is that there's a bigger change in x. And if it continues to get steeper, then you're seeing an even larger change in x. So you're seeing here that at this point, delta x is equal to 0. But now you're seeing a little bit of change. So if I look at this change compared to that change, you're seeing that the change is getting larger as I go up. So if I look at the slopes of these, what you're seeing here is that the slopes go from 0 to something steep. So if I was looking at my numbers here, you would see here is that this would be V1. That would be V2. That would be V3 if I'm looking at my curve here. So remember, I'm comparing these two to each other. And so if I was to now smooth out my curve, what would I really see? I would see that my curve would then be flat, and then it would go like this. And then as I look at each of these slopes, you're seeing that the slopes are getting steeper and steeper. And as they get steeper and steeper, therefore, I'm getting a higher and higher velocity. And that's what I mean by a curve. But what happens if I do the opposite? If I'm slowing down, then what I'm really seeing here is that I'm getting a point where it's looking something like this here. So I have a velocity that goes like this, like that. And let's say that even at this point here, we actually stop right here. Well, I'm seeing I have a high speed getting smaller, smaller, and then finally getting 0 at that point. So what do I expect of my curve? So let's go graph this. So if I'm graphing this, what I'm seeing here is that I should start off with what? A steep curve. So if I start off with the steep curve, then when I'm looking at my points here, let's say that I'm at the origin, I'm expecting maybe a curve that looks something like this. So when I look at my line, you could see that this is a steep curve right here. And that would represent, of course, V1, a nice steep curve. Now, I'm seeing that my curve is getting less steep. So if it's getting less steep, then my next dot should be a less of a steep of a curve here. And then you can see that I can continue to do this until finally it goes flat. So then I go less steep and then finally flat. So what you're seeing here is that my slopes are getting smaller until finally my slope is 0 at this point. So in this situation, we're talking about slowing down and plotting it like this. But in real life, we don't draw them so segmented. We come in here and we just say, okay, it starts off steep and then it goes flat. And so if I start to look at these slopes, I could see that this slope and that slope look like that. And that corresponds to these points right here.